happens to be. So without further ado, let's get our first presenter up here. The paper is entitled Parametric Wave Field Coding for Precomputed Sound Propagation, and the authors are Nikunj Raghuvanshi and Snyder from Microsoft Research.
All right. Hello, everyone. Welcome to our talk. The goal of our work is to design a fast and practical technique for sound propagation that is applicable to current games. So I'll start with a quick demo. So this is a game scene. There is a waterfall to your right, and there's a battle going on inside these walls to your left, and this is with our system on. So pay attention to the reverberation and occlusion effects. Could you turn the audio on, please, for the demo?
Scene. As we enter, the sounds of battle smoothly ascend, while the waterfall fades out. The battle's location is indicated by this box. Inside the cathedral, battle sounds are occluded.
So you get a nice cathedral reverb automatically, and the sounds also get occluded naturally. So let's compare to the default game engine, the occlusion effect on the battle sounds.
Let's listen to the difference as we turn our system on and off. Without it, we can even hear the distant waterfall through multiple walls.
So with our system, you get much more natural transitions in the loudness of different sounds. And right now, game audio designers have to do all this by hand. So let's look a bit into the physics of this problem. This is the same scene that you just saw in the demo. I've cut off the ceiling of the cathedral so you can look inside. And in the demo, we took a path like this. So what the game engine would do is they have strict time constraints. So they'll take the listener location, shoot a ray from source to listener, figure out it hits some geometry someplace, and do a standard reduction in volume. This, of course, doesn't take the complex geometry of the scene into account. So let's look at the shortest path, for example, in this scene. So the sound has to enter the doorway here, and sound wavelengths are large, so they tend to bend or diffract around edges. So there's one diffraction, a second diffraction, then it diffracts into the main hall, hits a small pillar, and gets to the listener. And there are other paths like this too. Like the one that enters through the other doorway, bounces a bit, then bounces in this little space a bit, and enters the main hall. So even if we wanted the simple effect of initial loudness of sound, even that involves a path integral that has a complex dependence on the geometry of the scene and where the source and listener are in the scene. In addition to that, for sound, we care about transient effects. So this corresponds to the feeling of reverberation in a space, which corresponds to much longer paths, which are weaker in energy and arrive later in time. So the sound, for example, might enter through this doorway, bounce here, bounce in this little space here, so get some reverb from that space, then bounce into the main hall, bounce around a bit, get to the listener. So there's a huge number of such paths in this scene, as you can imagine. And that gives us the feeling of high-order reflections and reverberation. And there needs to be some way to capture this to take into account the geometry dependence on this scene. What games do is some audio designer will draw a reverb volume saying this is a cathedral, whenever there's a listener inside it, use such and such reverb, which is of course really very approximate. There is a large body of work on interactive geometric acoustics, and the goal is to construct these paths efficiently in real time. But as you can imagine, this can become really difficult because in some way this problem is similar to global illumination because you have to account for so many paths. But with sound, one also has to take diffraction into account, which increases the number of paths, and also the phase or delay has to be taken into account. But if you can trace such paths in real time, the advantage is you can handle dynamic geometry. So what we do is a numerical wave simulation. So we do not construct these paths explicitly. So this is the same scene you just saw. I'm going to show you a 3D wave simulation, but I've taken a slice through it and I'm looking from the top. So let's put a sound source someplace here. And you immediately see a ground reflection coming up as the second wavefront here. Then the sound enters and curves around all these obstacles inside the cathedral and gets to this point A where you start registering a signal. Sound waves also diffract over this castle boundary and get to point B where you also start getting a signal now. So this signal that is received at a listener due to an impulsive source at the source location is called the impulse response. And this has a very strong dependence on where the source is and where the listener is. So in effect, this is a 7-dimensional problem. 3 dimensions for source, 3 for listener, and also it's a time-dependent signal. And so you can see that at point A, the sound is reverberating inside the cathedral, whereas at point B, it's already started decaying out because it's an outdoor location. So the challenge with precomputed approaches is how to store the 7D information compactly, because the raw data for a scene like this is 50 terabytes. And with our technique, we can compress it down to less than 100 megabytes. In related work, in comparison to related work that's quite close to ours, precomputed wave propagation stuff, we save more than 200 times memory and we're more than 10 times faster. So here's the main idea of our approach. So suppose you have the impulse response between 2 points in space. It's quite standard to divide it up into 3 portions. There's the initial arrivals, which a perception integrates into one single percept of initial loudness. That's called the direct sound, which is followed by more higher order bounces in the scene, which might contain reflections, scattering, diffractions. That's called the early reflections. And then there's the asymptotic decay of the final remaining residual energy in the scene, which is called late reverberation. So we encode this in terms of 4 perceptual parameters that approximate the energy decay corresponding to this impulse response in the schematic shown on the right here. So there are 2 parameters which correspond to the total energy in the direct sound and early reflections respectively. And another 2 parameters capture the decay rate of energy in the early reflections and late reverberation respectively. These parameters are based on an ISO document. So suppose we have a 3D scene, we have a source located as shown on the left here. We do a transient 3D wave simulation. We apply this encoding scheme I just described, and that converts this 3D chaotic wave field into 4 parameter fields, which are shown on the right. Again, I've taken a slice through the 3D field I'm showing you from the top. And the source location is as shown. So let's look at these in a bit more detail. So first up, the loudness parameters. So on the left, you can see the direct sound, and you can clearly see distance attenuation effects in it. Also, you can see strong shadowing effects like at the edge shown here. The interesting thing is with sound, even a point source will generate soft shadows because sound waves bend around obstacles and you're getting diffraction effects. So in comparison, the early reflection field is much smoother as shown on the right, and because it corresponds to more bounces within the scene, and it varies roughly with which room you're in. Now let's look at the decay rate parameters. So on the left, there's the early reflection decay rate, and the early reflection energy decays really fast in this scene so you can see it's all red. That's because it's an outdoor scene. So all the early reflection, the strong reflected energy just escapes out the top of the scene. But as time progresses, it leaves behind this weak residual energy that keeps bouncing between parallel walls and such structures, which is why the late reverberation decays very slowly in comparison. So we have converted a 3D transient wave field into these parameter fields. The advantage is these fields look very smooth in space, so they're very compressible. So this curve shows that. So what we do is we take horizontal slices of these fields and apply a lossless image compression scheme similar to PNG. And that already gives us a lot of gain in memory. So the black curve here is the uncompressed size, which of course scales with the volume of the simulation domain. But with our scheme, we get a compression similar to the bottom curves here, shown for 2 scenes. So the main thing to notice here is that the size of our compressed data is scaling with the surface area of the scene, so not the volume. So we already took away one time dimension by converting an impulse response to 4 numbers, and we've also taken away one spatial dimension now with our scheme. So we go from 7 dimensions to 5, which is the main reason for our compression. The second advantage of parameter fields, in addition to compactness, is that they are very fast to render. So let's say we have a source at runtime with some signal, as shown here. By looking at its location and looking at the listener location, we can decode the parameter fields, do some spatial interpolation, and figure out the 4 parameters that characterize the acoustics between the source and listener. For illustration, let's just focus on the early reflection. So we have an energy and a slope. So we need to create some kind of synthetic impulse response that obeys these parameters to convolve with the source sound. The way we do this is through what we call canonical filters. So let's take a quick detour and look into these. So these are 6 fixed impulse responses, 3 for early reflections and 3 for late reverberation. And they are specifically designed to have specific energy decay rates that cover a wide range of practical interest. Talking specifically about early reflections, these filters are designed so that when you interpolate between them, you smoothly get an intermediate response without any impulse response interpolation artifacts. And they're also normalized to have unit energy. Also note that the y-axis here is on log scale, so these are actually exponentials. That's why we use 3, so that when we interpolate between them, we get a good approximate exponential that's between them. So let's get back to the runtime system. So we have these 3 canonical filters for early reflections, because that's what we want to apply. And I've just drawn the energy envelope here, so it's a schematic. Based on the slope and energy we want, we can compute interpolation weights for these filters. And then we want to blend these filters in some way, which we do indirectly. So what we do instead is scale the signals by these weights, perform convolutions with these filters individually, and sum the output. This keeps the filters fixed. And the advantage is, suppose you had another source with its own set of parameters, and based on these parameters, its own set of weights. But since convolution is linear, we can sum up all these signals before performing convolutions. So the advantage is the number of convolutions no longer depends on how many sources you have. This is a huge gain, because convolution is far, far more expensive than these summations we're doing here. So this demo shows that our system can handle a lot of sources.
Making sense.
So there are like 20 players in this scene, all making 2 or 3 different sounds. This demo shows that we can handle fast-moving sources without any spatial interpolation artifacts.
Artifacts.
At the end, you also hear some subtle reverberation when you pass indoors. So this demo shows that there are water sounds beneath this pathway in front of you. They're reverberating in the space, and the walls around the doorway are blocking that reverb sound.
Note the exclusion effect and the impression of distance as we switch our system off and on.
So this shows a very tough case. Sounds are reverberating inside a hall that you will fly through, lots of players fighting in there. And the sound has to bounce around in that hall, diffract and bounce around this little cave-like passageway, and finally get to the listener outside. You also get a 3D occlusion effect at the end from the roof. So audio designers have to do all this by hand right now. Finally, this scene shows a lot of these effects in a single scene.
Note the change in reverberance as we move into a narrow space that traps sound waves. In comparison, the outdoor courtyard traps less acoustic energy and sounds more open. As we move back outdoors, note that the waterfall sound ascends naturally. As we move away, the sound recedes. Here's what it sounds like turning our system off and on.
So in conclusion, our main idea is to take transient 3D wave fields and convert them to perceptual parameter fields. There are two advantages from this. First, these fields are compact, they allow us to go from 7D to 5 dimensions, and secondly, they are very fast to render. In future work, we'd want to improve realism. This set of parameters is by no means complete, so we'd like to capture directional reverberation effects, sound diffusion, spectral filtering, and also outdoor acoustics is a big open area. There's limited literature on how to parameterize outdoor responses and also handle echoes. I'd emphasize that our simulations contain this information, but the challenge is how to encode that information compactly and render it fast. And finally, we'd also like to handle some dynamic geometry like doors and windows, but it's a precomputed approach. So dynamic geometry is the most challenging aspect. Thank you.
So we do have a few minutes for questions if anyone wants to come up to the mic. And in the meantime, maybe I'll ask a question. So you mentioned at the end there, looking forward towards integrating directional effects. So can you talk a little bit about what that would allow you to do and what obstacles kind of stand in the way?
Yeah, so, okay, oops, sorry. So, yeah, directional effects mean that the direction the sound is coming from, you need to render that because we have a stereo perception. So we want to render the whole reverberation, like if it's coming from a wall next to you, if a reflection bounces off of that, you want to render all that. And the challenge is that all that angular information, there's a lot of information in there. So we need to store all of that nicely somehow. So we can extract it from the wave field using energy flux, but the problem is how to compact it down. Yeah.
Is this on? Oh. So as you move through the space, you're varying those coefficients that feed the convolutions. And I'm wondering, how are those coefficients generated? Are those like automatically generated based on the space?
Yes, that's the whole idea. So as the source and listener move, we do decoding and say, okay, these are the 4 parameters, right? This is the amount of energy and energy decay we want.
Right.
Based off of that, we figure out the weights for the convolution filters.
So those are all pre-computed and basically a 3-dimensional spatial map.
Yes. So the parameter fields are pre-computed, and we just keep them stored.
Very cool.
Yeah.